I'm very, very pleased to be here. It's a wonderful community. It's wonderful, wonderful not to have to excuse oneself whenever one addresses problems that are a little bit more philosophical and foundational. So thank you very much for the organizers for inviting me. What I would like to do is present quantum mechanics as a theory of inference. So the question that runs in the background of all of this is, do the laws of physics reflect laws of nature, or do they reflect rules for processing information about nature? Of course, all these rules process information about nature anyway, but the idea is that here we're going to have to keep the ontological aspects and the epistemic aspects sort of separate and clearly distinguishable. So the objective here is going to be to derive quantum theory as a form of entropic dynamics. And in the process, discuss some implications for the theory of time, for quantum measurement, for Hilbert spaces, and it may very well be that towards the end, I'm not going to have time to address many of these issues in detail. Well, so be it. Very well. When I say that the laws of physics are rules for processing information, then the natural implication of this is that the actual rules for processing information, which are not arbitrary at all, impose strict constraints on the actual forms of the laws of physics. So it may not be a bad idea to start by giving a one-slide overview of entropic inference, of the use of entropy as a tool for inference. So first of all, we have to decide what it is we're talking about, what are the variables that we are uncertain about and we want to infer. And then we're going to put probability distributions on those variables. And the idea here is this is the space of all possible probability distributions on those variables. The point of entropic inference is that what we actually know or don't know about these variables is expressed by a prior probability distribution. And then we acquire some information. The information in this approach is a constraint. Basically, what's going on here is something along the lines of, we believe, or this represents our current beliefs. Someone tells us, no, you dummy, you should be believing something in there, and our problem is to pick one of these probability distributions that will constitute the update from the prior to a posterior. So now the question becomes, how do we pick one of these very many probability distributions? It takes a fair amount of arguing, but one can make the argument that the right way to do it is to rank all probability distributions in this space according to a certain criterion that's given by the relative entropy. The maximum of this relative entropy lies precisely at the prior, and so here we have the lines of constant entropy. As they decay away, they sort of measure a distance away from Q. When we then proceed to do the inference consists then in maximizing the entropy subject to the appropriate constraints. The point or the probability distribution that actually maximizes the entropy is the one that has, well, maximum entropy within this region. That's the posterior. That's the update. But this approach does something better, and that is the following. We can always ask the question, well, what if you're going to make the update from the Q to that P, but what about all those probability distributions that have entropy that's very, very close to that of P? What about them? Are you totally sure you should neglect them? Well, we can ask, what is the probability that instead of choosing that P, we should have chosen probability distributions within that region? And the answer is that the probability of landing in any volume element in this region is going to be given by the exponential of that relative entropy. So we prefer that P exponentially over other probability distributions in that region. One of the nice things about this method of inference is that it includes the Shannon, Jaynes, Boltzmann, Gibbs methods of doing statistical mechanics. It also includes Bayesian updating as a special case. And as this formula shows here, it also includes the theory of large deviations. Indeed, when the actual constraints, the information, is in the form of, for example, expected values, we recover exactly what the Maxent method accomplishes. When the actual constraint includes information in the form of data, that is Bayesian inference techniques. Anyway, so this is entropic inference in one slide. Clearly, there is way, way more to be said and explain and justify all of this. But let's start then the problem. We're trying to do quantum mechanics. We have to decide, and this is one of the most difficult parts of the whole enterprise, we have to define what it is we're talking about. So there is the whole world. I'm going to be interested in talking about a system which may be particles or fields. As I proceed, in general, I'm going to be talking about n particles. Soon enough, I'm just going to restrict to a single particle in 3 dimensions, just for the purposes of talking quickly and giving you the idea of what's actually going on here. But we can actually do the same framework of entropic inference on fields, and I have done that. So the idea is, this is a framework for developing an entropic dynamics that can be applied to many different types of objects. Very good. So the world contains a system of interest, but it also contains other stuff. There exist other variables that are relevant to what we want to say here. It could be that those variables are a background field, an electromagnetic background field, maybe a gluon background field, a background field. It could be that these variables reflect a space-time foam. One of the things that I want to pursue here is I'm going to keep silent about what these variables are. There is an advantage to doing that, which is that as long as I keep my mouth shut, I can't be wrong. I am sure that that does not address all the questions that you may want to ask about those variables. That's another question, all right? Let me put my problem from a different perspective. Suppose that you're interested in the statistics of throwing dice. It is actually true that you can figure out, in principle, the statistics of throwing dice by studying the quantum mechanics of how dice roll. Just do it properly, use a lot of computer time, and you can figure out precisely what the outcome of throwing a die would be, and then you can do some kind of statistics over it. You can do that. The remarkable thing is that you would be keeping track of a lot of details that, for the purposes of figuring out the statistics of throwing dice, are irrelevant. It doesn't matter if your die is a perfect cube with sharp edges or round edges, or whether the viscosity of the air is a certain value or another. Keeping track of all of these details is fine, if you can, but for certain questions that are irrelevant, we can throw them out. So think about my approach to quantum mechanics as not keeping track of all the details that may be important for some questions, but not for others, okay? I'm going to be throwing away from the very beginning all of those irrelevant details, or all of those details that are irrelevant for the purposes of deriving quantum mechanics. For example, in the case of the die, all you really need to know is that the die has 6 possible outcomes, and that, as far as I can tell, I have absolutely no reason to prefer one over the other. I have thrown away an incredible amount of information there. I am just focusing on what's relevant. My hope is that by focusing on what's relevant there, that will provide a foundation with which every other theory of a sub-quantum mechanics should agree with. Very good. Let's go, because there is a fair amount of material to cover. Very good. Here's the subject matter. The goal is to predict the positions of particles, X. The particles have definite but unknown positions. Now, you can see here that I am deviating from the standard approach to quantum mechanics. When these particles go through 2 slits, they either go through one or through the other. This is what eventually is going to solve the measurement problem for me, because events here are already definite from the very beginning. These particles have definite positions. Now, this position, let me see. I'm also going to assume that there exist other variables, y, and I'm going to assume that these variables are known, so they are described by a certain probability distribution, py, and that probability distribution, the probability of the y variables, depends on the positions of the particles. Remarkably, I don't have to tell you much about what those y's are, and I do not have to tell you very much about what this probability distribution is either. What I will have to tell you is that these probability distributions have an entropy. And as you can see here, the entropy of these y variables depends on what those positions of the particles are. Now, right here, as I proceed, I'm going to point out the consequences of these various ideas for the ultimate formulation of quantum mechanics before I get there. So what do we see here about quantum mechanics already? Well, one of the things that we see here is that the particles have unknown positions, and what that means is that I'm going to have a probability distribution for them. This is what describes the fact that these positions are unknown. And in fact, since I'm doing a theory of inference, the fact that these positions are unknown is the natural thing. Whenever you deal with anything in the world, the natural situation is one in which you do not have enough information to make precise predictions. Indeterminism is the norm in a theory of inference. What requires an explanation is determinism. Indeterminism is what one should expect. Here, my problem is going to be precisely the opposite. How is it that there are certain situations out there in the world where we actually have enough information to make precise predictions? Very good. Second, there is this entropy here of these y variables. Eventually, that entropy there will morph into a second function. So what we are seeing here is that to each point x, I have 2 degrees of freedom, 2. One of them describes a probability. The other one is connected to an entropy. And this is what's going to explain why it is that in quantum mechanics we use complex numbers. In fact, this phi here will end up being the phase. All right? So there is a reason why we use complex numbers in quantum mechanics, why we have 2 degrees of freedom. The reason is that we have the objects that we're interested in, and there is something else out there that can have influences over what we're talking about. Very good. I wrote here that y variables are not hidden variables. But I want to be very clear about this. They are hidden variables in the sense that we do not see them right now. We do not know what they are. At this point in the development of science, they are hidden. However, one of the main reasons why people introduced hidden variables in the first place was to make physics look more classical. Either you would make quantum mechanics, quantum probabilities look like classical probabilities, or you would make quantum mechanics look like classical mechanics. These variables don't do any of that. These variables are just something about the rest of the world that has an influence on our inferences. Very good. So here's the dynamics. We start with the configuration space of the particles. So this configuration space is 3-dimensional for 1 particle, 6-dimensional for 2 particles, infinite dimensional if we're talking about fields. And you can see here that right from the beginning, I'm putting into the theory the fact that there is going to be a strong non-locality. In this kind of theory, non-locality is the norm. The question is, under what circumstances do we recover local behavior for, say, the classical limit? Now, to each x, there is a probability distribution for the y's. And since to each x there is such a probability distribution, we would like to think about the set of all of those probability distributions, one point associated to each point down here. So there is an associated statistical manifold. Very good. Now here comes the main dynamical law of evolution. Change happens. I do not explain why things change. I just take it for granted that change will happen. Just like in classical mechanics, you do not have to explain how it is that a particle, that's a free particle, will continue in its state of motion at constant velocity. You don't have to explain that. You just take it as the foundation for classical physics. Here, I'm going to assume that change happens. So there will be a change. My job is going to be to figure out in what direction this change happens and how probable it is that the particle is going to jump far away or close by or whatever, right? We're going to try to figure out what change happens. But the fact that changes happen is the beginning. Of course, when you change from x to x prime, the probability distribution of the y variables also changes to py prime. Very good. So here is how we figure out how entropic dynamics works. We're interested in the new x prime and the new y prime. And so the idea is going to be to maximize the joint entropy. So you see here, the probability distributions here are of the joint x prime and y prime. That's what we're integrating in. This is the prior. We're going to maximize this to find out what the posterior is. And to start, we need a prior. Where does the particle go? I have no idea. Okay? So this is the beginning. When the particle jumps, it could jump anywhere. So the prior that I'm going to use here is that the probability distribution is going to be uniform. This is a symmetry argument. It's not unlike saying that we start with a die, and the die has 6 faces, and we have no idea how to prefer one over another, all right? All problems of inference will eventually, at some point, rely on some such symmetry argument. Here is my first symmetry argument. I have no idea where it's going. Okay, so now, how do we constrain the possible probability distributions? Well, I'm going to separate this guy, we can always do it, separate this into 2 pieces, the probability of x prime and the probability of y prime. And here's my first constraint. The probability of y prime will remain on that statistical manifold. So it's a probability of y prime given x prime. I'm actually saying here that this probability distribution of y prime does not depend on the x. How about the other piece? That piece there. Well, this is really what we want. This gives you the probability, the transition probability from an x to the next x prime. And here I'm going to use a rather physical argument, or rather a physical constraint. I'm going to say when x, the particle at x jumps, if you don't give it much time, it's not going to go anywhere. So no, we don't have a notion of time here. So what I'm going to say is that the particle could, in principle, travel very, very, very far away, but only provided it makes lots of little steps in between. So things can move far away, provided they go through intermediate points. So what I'm going to say about this guy here is, I want to focus on short steps. And I'm going to impose that the particle doesn't move very far away by saying that we have a constraint on the expected value of the distance traveled. This expected value is some small number, and I'm going to determine that later. Very good. So we have our prior, we have our constraints. All we do now is maximize the entropy, and here is the result. The result for the transition probability is the exponential of the entropy of these y variables. And here we have the constraint on the short steps. There is the distance. Alpha is a Lagrange multiplier that for short steps, alpha is a very large number. So what this reflects is the fact that as you jump from x to x prime, you're going to tend to jump in the direction in which you maximize the entropy of the y variables. You're climbing up an entropy gradient. And on the other hand, this other term here says that you can't really go very far away. So these are short steps. If we look at what the actual displacement is, what we find is that there is an expected value. The average displacement there, the expected drift, is going to be in the direction of the gradient of that entropy. So the expectation is that you're going to drift up the entropy gradient. And then there is a fluctuation. And the fluctuations, once you work them out, are something that has to do with the inverse metric of the configuration space. So essentially here you have the variance, and here you already have something interesting. Alpha is the Lagrange multiplier that implements the short step constraint. We have something interesting there. The interesting thing is that the expected drift is proportional to 1 over alpha, a large number, short step, while the fluctuations are proportional to 1 over the square root of alpha. So that means that the fluctuations for alpha large completely dominate the expected drift. So the sort of trajectory one expects here is very much like a Brownian motion. That's what it is, in which the trajectory is going to be continuous. You can see that the steps are very, very short, but completely non-differentiable because the fluctuations dominate the dynamics completely. So it's continuous, but not differentiable. Okay, very good. So now we have, whoa, okay, I have to hurry. That means I'm going to have to chop the end, okay? This is the dynamics for a single short step, right? But if you start doing many of these steps, then we need to figure out how to compute the cumulative effect of many such short steps. Now, it is at this point that we introduce the notion of time. The foundation of the notion of time is the dynamics. And the dynamics is contained in those short steps. So time here is going to be introduced as a tool to keep track of the accumulation of many such small steps. The idea is the following. If you have the joint probability of an initial x and a final x, and you integrate over the initial ones, you get the probability of the final step. And we can always rewrite this in this way, right? Just use the product rule, fooling around the probabilities. Now here, this is true, period. These are rules for manipulating probabilities. We have no choice about that, right? I'm not making any Markovian or Chapman-Kolmogorov approximation or anything of the sort. This is true, period. But now I'm going to make an assumption here, or rather, I'm going to construct something weird. I'm going to say, well, look, if this is the probability distribution of the x's at one instant of time, because this tells me how I'm going to jump to the next positions, I'm going to make the assumption that this means the next instant of time. I'm inventing the notion of time here. That's why I didn't call it, as you see, I didn't call it time. I called it entropic time, because in principle, this has nothing to do with real time. This is just, I'm doing my inference, many steps. So I'm going to rewrite it. What I'm doing here is I'm introducing the notion of an instant. What is an instant? An instant is a probability distribution. Given this instant, I can propagate it to and create the next instant. Given the next instant, I can plug it in back there again, and I am creating from one instant, I build the next one, and the next one, and the next one. I'm building time as a sequence of ordered instants. Remember how we got this transition probability by maximizing entropy? I'm never minimizing an entropy. It's always maximum. So there is an order to this time here. So we have a set of instants that are ordered. This entropic time is naturally ordered. There is an arrow to it. Very well. Finally, in order to complete the creation of this entropic time, we have to talk about how much interval, what is the separation between these successive intervals. And the idea is always time is given by the dynamics. Now, for large alpha, the dynamics is all in the fluctuations. Remember, the drift didn't matter. It is much smaller. So if we look at the fluctuations, here's the covariance. What I'm going to do is I'm going to define the duration or the interval between two successive instants so that motion looks simple. Time is defined so that motion looks simple. And in this particular case, I'm going to say that alpha, the Lagrange multipliers that tells me the size of the step, I'm going to define the time interval in such a way that they're connected in this way. So you can see that for a really tiny, well, really huge alpha corresponds to a very small delta t. Tau is just a constant here so that t has units of time. If I substitute that there, I have several things that are interesting here. First, you can see that this variance goes like delta t, all right? Now, if you look at classical mechanics, the foundation of classical mechanics is that time is defined in such a way that if you have a free particle, equal displacements correspond to equal increments in time. That's the clock that is used for classical physics. In quantum physics, the clock is equal intervals correspond to equal increases in the variance. It is the fluctuations that provide the clock in quantum mechanics. The other thing that's sort of interesting is that, well, I cheated here. I introduced already some of the constants that come from that tau and from various other places. But one of the other things that you see here is the mass of the particle is something that is a measure of fluctuations. In classical physics, mass has something to do with resisting acceleration and all of that. Well, here it has to do with measured fluctuations. Very good. So here we have our problem, or rather, we have our equation of motion. It's there. It's an integral equation, and we can transform it into a differential equation, the Fokker-Planck equation, which is just probability conservation. So let me do that. When I actually transform my integral equation into a differential equation, I find that the velocity with which probabilities evolve is essentially the gradient of a scalar function. That scalar function has two pieces, one of them being the entropy of the y variables, and the other one is something that has to do with the log of the probability distribution itself. So there are two pieces. Accordingly, that velocity has two pieces too. And here I'm using notation that is borrowed from Edward Nelson. The idea here is that there is going to be a drift velocity, which is the gradient of the entropy, and there is going to be another term, the osmotic velocity, which is the gradient of that log rho. And you can see it is osmotic velocity because when you look at the actual diffusion current, rho times this u, you see that there is a minus, and it's proportional to the gradient of rho. So this is Fick's law with a wacky diffusion coefficient. So it's just diffusion. Now, quantum mechanics arises from the collaboration of those two probabilities. Very good. Here we go. Now, if you have the quantum mechanics of these things here, for each x, there is an entropy. And if you do the diffusion, this is what you get, which is not quantum mechanics. All right? It's not. Now, whenever you're doing inference, and you get a result that's rubbish, this is not rubbish, this is a different problem, the natural conclusion is that you got the wrong constraints. So I'm going to change the constraints to make this look like quantum mechanics. The solution, here is our configuration space. We allow the statistical manifold to be dynamic. We allow it to wave around. And when you do that, you see that you're talking about particles, but there are waves in the picture. And the precise dynamics that I'm going to choose here is one in which there is a conserved quantity. This is, I believe, the most interesting conclusion of the stochastic mechanics of Nelson. Diffusion is a much, much more richer phenomenon than we tend to think. That you can have, if you impose conservation laws, you can have bumps and minima and maxima and all sorts of things. So let me do that and see how we conclude this. I'm going to impose an energy conservation. Here's the energy that I'm going to write down. The energy is going to be a functional of rho, of the probabilities, and of the entropy. And I'm going to write the energy in terms of, well, this is for non-relativistic physics. There's going to be, so if I do a Taylor expansion, the lowest terms are going to be something in the velocity. This is the current velocity. Something in the osmotic velocity, maybe a potential. If we impose that this be a constant for arbitrary choices of the initial rho and s, then this leads to the quantum Hamilton-Jacobi equation. And as you see, I'm done. Now, there is an interesting feature here. I was talking about particles having positions. The positions are real. But when you look at this energy here. Here there are entropies. There are rhos, there are probability distributions. The energy, is not a property of the particles. This is a completely epistemic object. It is a tool for making inferences about where we're going to find the particle, but it is not a property of the particles. Anyway, let's finish with this. The result is two coupled equations. One is the Fokker-Planck equation, probability conservation, really. And the other one is the quantum Hamilton-Jacobi equation. And what we see here is that phi, the entropy of the y variables, tells rho how it should evolve, while on the other hand, rho tells phi how it should evolve. These two are coupled to each other. Very good? Nothing prevents us from combining those two degrees of freedom into a single complex object, and of course, the result is a Schrödinger equation. From there, we get classical mechanics and everything else. The fact that we have complex numbers here, or that the Schrödinger equation turned out to be linear, or that once we see that this is linear, we're going to find that Hilbert spaces are very useful. This is extremely convenient, but it's not fundamental. If I had chosen a slightly different form for that conserved energy, all of these things could go haywire. There is absolutely no reason that if I try to do, say, quantum gravity, it's going to end up being quantum. We have to figure that out. Very good. I want to stop here.
Okay.
Yes.
Thank you very much. So, one short question. Yes. Here's a microphone.
From where the Planck's constant come about?
When you actually figure out what the geometry of these, say, for example, the configuration space is when you have several particles, or
There must be some assumption.
of course. For example, I never told you here, when I pick this energy, and I say, well, it's quadratic in this, quadratic in that, how are those coefficients? What coefficients do you pick there? There is no reason why the coefficient there and the coefficient there should be the same, right? And so if I actually say this is A and that's B, then I realize that as I work further with this theory, I have an incredible amount of freedom of rescaling one, rescaling the other, right? And so there is essentially a constant that emerges at some point. And because once I get to the very end, I can see, this constant here is what people normally measure from the Schrödinger equation and say it's the Planck's constant. So there is room for fooling around with these things here.
To fool around, yes.
Yeah,
Okay.
yeah.
You're good, so.
Oh, no. It's fooling around, but in a very controlled way.
Sure.
Okay?
Okay, then let us.
Very good.